Welcome everybody for this new seminar. Today we will have the talk by Dr. Ignasi Pérez Rafols from the Universidad Politécnica de Cataluña. He will talk about the galaxies hiding in the forest as a new BAO tracer and others applications. So Ignasi, he got his PhD on the University of Barcelona. Then he moved as a postdoc to Marseille in the LAM laboratory, then in Paris, and then he returned to Barcelona as a postdoc at Marie Curie in the E5. And after that, Maria Zambrano postdoc also in the University of Barcelona. Now he has a staff position as a lecture professor at the University Politécnica in Cataluña. And he worked mainly in studies on correlational functions of Lyman alpha and all the stuff that is around. So he's working with the data on DESI and WIB, ESO, and for extension on GPAS data. So thank you, Ignasi, very much for this accepting this seminar, and the floor is yours.
Yeah, so thanks. This is actually my second time coming to Granada. One was in the SEA. We were discussing with the people in the room like a few months ago. But today I wanted to talk about these galaxies that are hidden in the Lyman alpha forest, to be precise. That basically it considers a sample that we seldom have information. We have all the data, but we still not exploiting it because we are not sure we can find them. Right, but in order to understand this is going to be sort of, the title is going to be towards the end of my talk. I want to explain what the Lyman alpha forest is first, and what is BAO, how we use it to measure the expansion of the universe, and maybe this is going to be a little bit different from what the title suggests, but this is going to be a necessary step in order to understand what we're trying to do, identifying these galaxies. So just as a brief outline, if this works. There you go. So I'm going to be introducing what's cosmology in case people from different backgrounds, so that we have everybody on the same page, and explain what is Lyman alpha forest, and as I said, how to measure BAO, right? And then, as I said, these galaxies in the forest will be sort of one of the last points of the talk. Right, so let's get straight to the context. So this is a picture that you've probably seen many times, the LCDM model. The idea is that we have a very hot, dense universe at the very beginning that somehow explodes and starts expanding. Right, so we have these tiny fluctuations that grow quickly, and then at some point the dark matter decouples from normal matter, but this creates like a distribution already that will be planting seeds for where galaxies will form in the end. So then as time goes by, maybe better if I point with the mouse, as time goes by, at some point the photons decouple with the barrier, with the normal matter, let's say. And this causes the cosmic microwave background, right? So we've heard a lot about this. This is sort of like a snapshot of the universe at the time, and also has like an imprint on all these fluctuations that have already grown a little bit. So as time goes by, the universe keeps expanding, and the fluctuations keep growing. At some point, you reach critical masses, and you start to form stars and galaxies, and so on. And then the history continues, and we believe that at some point something called the dark energy enters into play and accelerates the expansion of the universe. Right. So one of the mysteries of today's physics is that we don't really know what dark energy is, and this is one of the things that we're trying to understand. Right. So in this standard model, this is sort of a constant thing that appears somewhere in the near past. But there are other models, extensions to this model that suggest that it could have like a dynamical evolution, right? We're not gonna go into much detail into these models, but just the idea is that the expansion of the history, sort of this delineated by this line here. So how fast things grow, and it's telling us a lot about the model itself. And if we can measure the expansion at different times, then we can reconstruct the whole model and say, okay, so now my cosmological model is this way, that energy is behaving this way or that way, right? So the question is then, how can we measure this? And one of the answers, because there are many possibilities, is the baryon acoustic oscillations, or BAO. So take a picture of the CMB here at the very bottom. So as I said, this is the snapshot where photons and baryons decouple. At this point, there is a characteristic scale produced by the sound wave, the propagation of sound waves in this hot mixed medium that is imprinted on this photograph. And then this scale keeps up. We sort of lost the image for some reason here in the room. There you go. Now we're back. So this scale remains imprinted as the evolution goes back. So remember that, like here, gravity is leading, is driving this growth of fluctuations, right? And the regions where we have an excess of fluctuation, an excess of mass, will grow and will have more mass. And regions that are less dense will become even more and more dense, creating voids later on, right? So then there are these tiny areas here, these characteristic scales, where we have an excess of an overdensity, an excess of probability of finding pairs of galaxies, for instance, that is a standard ruler. And we can use this to trace the expansion of the universe. And that's what we do with the baryonic acoustic oscillations, right? So there are two main ways to measure this BAO. One is with counting pairs of galaxies. So we say, here I have one galaxy. Like for instance, let's say we can take this one. We have one galaxy, and I just measure at different distances, so how likely it is that I find another galaxy. And I do this over the entire sky, and I can construct the power spectrum, and I will see an overdensity at this characteristic scale here, right? Which is called the sound horizon. So then the other way to do this is using the Lyman alpha forest, which I'm going to talk a little bit more about now. So the idea is that you have very bright background quasars that are shown here in this animation that I'm going to play. These are very powerful galaxies, but what we're really seeing is the emission by the jet produced by the accretion towards the supermassive black hole in the middle, right? So at this very high redshift, we cannot see the galaxy emission, but just the emission from the central black hole mass. If you get closer on redshift, and this is something that I've worked with Finesse, there is sometimes some this mixture because you start seeing both things, and then classifying these objects is rather difficult. But the idea is that we have this, and we are not so much interested in the objects themselves, but what lies between the objects and us. So the idea is now that the rays are traversing the universe, and they're encountering, going through the intergalactic medium, they're going through the circumgalactic medium, and sometimes through galaxies. And this crossing of gas is leaving an imprint on the spectrum that we can see here. So you see here, this big line is the Lyman alpha emission line, and you can see there are a lot of absorptions to the left, right? These are caused by the redshifting of the lines, like the hydrogen atoms are always absorbing at the Lyman alpha wavelength, but the expansion of the universe is driving these wavelengths longer, so we can observe a series of transitions that are not noise, but contain information. This allows us to sort of map the three-dimensional, make a map of the gas, right, in the universe. If we have many lines of sight, then we can do we can do the same technique that we're saying about BAO to measure the expansion of the universe. So let me just Move on. Why is it not? Was it there? So this is just another example, a static example of a high redshift quasar, high signal to noise. So redshift is 3.2 for reference, because I know that depending on who you talk to, high redshift means completely different things. So here, just to put things, we consider high redshift quasars above 2.1, because that's where the Lyman alpha line enters the optical spectrum, and we can get information from ground-based telescopes here, such as the one for SDSS, DESI, and now we'll observe shortly. So then you can see again here this in this very high signal to noise spectrum, you can see the absorption caused by the Lyman alpha absorption. But then you can also see there are other lines, right? So here this would be Lyman beta line, and you would have absorption here. In this purple bit, you would have Lyman alpha absorption, but also Lyman beta absorption. And this is somewhat mixed, and we can really, it's completely degenerate. We cannot tell apart one from the other. And this is something that we need to model when we're measuring things, right? Of course, we also have other metals. So we have this, for example, the carbon-4 line, or the carbon-3 region here, with the carbon-3 line is not appearing in this spectrum, but it lies a little bit more toward the right. And you have, as you can see, like for metals, the absorption is not as strong. That's simply because there is not enough metals. Hydrogen is everywhere. Metals are much, much less common. So what is it that we measure exactly? So here is like a cartoon imagine that we have like sort of one hydrogen cloud over there, and another line of sight, we have another hydrogen cloud. And what we do is measure the distance between the two, right? So in reality, what we measure are angles and redshifts, and we need to convert them to distances in order to be able to measure the characteristic scale I was talking to about at the beginning. So now we need a fiducial model. So we assume a cosmology that is close to what we think is the true. It doesn't really matter if it's exactly the true or not. So long as it's not like 10 sigma away, we are happy, we're fine with that. And then we look for variations on this scale, right? So if we got the perfect cosmology that we use for to this translation, then these parameters alpha parallel and alpha perpendicular, which are related to the Hubble distance and the transverse moving distance, they would be 1 because we've nailed it. If we just take something that's just a little bit off, the position of the peak will change, and we will be able to know that because the alphas are not 1, right? Of course, you will see that all the measurements are divided by this RD, this sound horizon, this characteristic scale that I was mentioning before. Because what we are measuring is the size of the standard ruler, and we need to anchor it somehow. So we need to know the size at some point, and once this size is known, because it's a standard ruler, then we can move in and get all the measurements. So this typically is set from CMB measurements. For instance, for example, you could have Planck do this, but you could also use other probes like Big Bang nucleosynthesis probes to have like independent estimates from CMB. In any case, you will always need some anchor, right? This is important. And another important distinction, even though we've drawn here in this cartoon sort of clouds of gas, we need not think of these clouds as individual components. So this is something that I'm asked very often when I'm doing these talks, is like, oh, so why is the methodology very different compared to galaxies, right? Because galaxies are discrete objects. We have one galaxy here, one galaxy there. Whereas here we have a continuous amount of clouds, right? It's not one single cloud, but it's a continuous field, right? This cloud thinking, it's easier for us to visualize it, but we need to keep in mind this distinction. Now, what we're measuring is these delta fields, which are fluctuations over the mean absorption, right? So these are absorption. And one of the main problems that we have is that we don't know what was the true emission, right? Imagine that we have like a very dense universe and you have very bright sources, and then all of them are almost all the light is extinguished, and then in some places a little bit more, a little bit less. This would have a similar effect as a very not like dense universe, very sparse universe with only big tiny bits of absorption here and there. So the overall absorption we cannot know, but we can know the fluctuations over the mean absorption, right? These are characterized with these deltas here, and we then just measure the correlation functions, right? So now I'm going to show you what are the latest results from these measurements. So we have the DESI 2. These are sort of the most recent measurements from a few months ago, which are using 800,000 spectra from Lyman alpha first, right? And over 1.2 million quasars. And then before DESI, the state of the art was like EVOS. Just for reference, I'm also quoting the number of objects they had, and you can see that we are in like 3 years of observations, we've more than quadrupled the 10 years of observations from SDSS. So what does the measurement look like? It's something like this. So this is Lyman alpha autocorrelation. You remember that we are correlating these deltas. So now what we're doing is we're putting them in bins of separation. So I'm taking the delta here and saying, so how much absorption is there 4 megaparsecs apart in both the transverse and the perpendicular separation? So these are really 2D measurements, but now we compress this information in these 4 wedges or plots that show the average on different chunks, right? So in blue here, we have the chunk that's closest to the line of sight. This mu is the angle, the cosine of the angle with respect to the line of sight. So we go very close to the line of sight, and then this red we have very far from the line of sight, right? So you can see this band here around 100 megaparsecs is the characteristic signal that we're looking for, the BAO position. And this black line is sort of the model, the best fit model that we have. But we have to keep in mind that we are fitting in the 2D space, and we are then also projecting the model. So sometimes you will see that there are some like groups of points that are a little bit consistently below the model, but that's because we are just taking everything in the 2D plots. And this sometimes a projection effect, sometimes that could be something else. You can see that there are other peaks that are present only in the line of sight. And these corresponds to this problem with the metals that I was mentioning before, right? So you can see that our modeling is correctly explaining this absorption. This is when we are assuming that we're having Lyman alpha absorption, but instead it's like silicon 4 or carbon 4 or other things, right? Normally, this is one of the lines of the silicon 2 line in concrete. Okay, so then with this, we can also add some like non-physical broadband terms that that will help in going explaining the points better. You can see this is in dashed lines, but the main end goal would be to not have to add them, because this would mean that we have a physical control of everything. One thing that's worth mentioning here is that we are stopping the fit here. We don't go all the way there because we are fitting using linear model. And if you go to very close distances, then nonlinearities start to appear, astrophysical effects start to play a role. And this is something that's not fully understood and we cannot use in our fits currently. So one of the goals would be to push this limit to closer distances, and this will help us include in our modeling more effects, like galaxy accretion of gas or stellar like winds from supernovae or these kind of things. This will surely have an impact when you are exploring very close pairs or very small distances. One other thing that we have to keep in mind is that this measure is shot noise limited still. We're reaching the point where this might not be true anymore in the near future. But for now, we're still shot noise limited, which means that if we could sample the same gas in another way, we could still gain extra information. And that's what we do in the cross correlation with quasars. So instead of taking the Lyman alpha and correlating it with itself, we correlate it with the positions of quasars. And you see something that looks completely different, but not quite so. So again, the coloring scheme is the same, still a 2D plot, but now you can see instead of a peak, we have like a trough, right? This is expected because the sign of the bias in Lyman alpha forest and quasars is opposite. So we have more Lyman alpha signal when we have more absorption, when there is more gas. So having like a very small delta, like a very small fluctuation, like lower values of the delta, implies more material. And then when we have quasars, if you think of a binary system, it's like it has a positive bias, 1 when we have the quasar, 0 when it's not. And since both are bias tracers of the same Dharma distribution, we can still gain some information here. But the peak, the only difference, the peak converts into a trough, but that's it. The position is more or less the same. And then what we do is we take joint feed. We take both correlations and we feed them simultaneously. So that's also why you may think that maybe some points are a little bit off. It could be understood because we're feeding not only these 4 points, but the ones I showed before, plus 2 extra in the Lyman beta region. Remember that I showed you like the picture of the quasar before, right? So we have on this one. So we have, this is our main region, but we also feed the correlation in this region. So we have 4 correlation functions, and here I'm just showing but 2. Anyway, what we can measure is the combined feed. So we measure the Hubble distance, we measure the transverse moving distance. And we can see here, I've added 2 panels from this DESI paper. The first one is the alphas. Remember, these alphas were these objects that were telling us how close we had guessed the fiducial cosmology. And the closer we are to 1, the more we are close. If we are far away from 1, it means that we got the wrong initial fiducial cosmology. But it looks like it disappeared again. Right. So it looks like our measurements are consistent with what we are finding. And then they are also plotted the measurements from SDSS, from EBOS DR16. And there was before some mild tension with Planck measurement, which is the fiducial cosmology that we are assuming. And it looks like it is somewhat going away, right? And then just maybe to have a more physical plot, I've also added this secondary plot here where we are plotting directly the Hubble distance and the angular diameter distance, or transverse moving distance. And I'm plotting them for BAO and also for other probes like CMB here, LCDM, or CMB plus the S5. And you can see that there is some agreement. Okay, so now we have the measurements from Lyman alpha. This is sort of that 1 data point. And we were saying that we wanted to have the entire history of measurements. And this is, then we need the help from other probes like galaxies. And this is something a little bit what we're doing here. So this is sort of a schematic plot just to illustrate the process. So we have Lyman alpha measurement here is covering this, sorry, with the mouse, maybe for those online. So it's covering this region here. But then we have other types of galaxies. Quasars themselves have another data point here. And then we have ELGs, luminous red galaxies, bright galaxy sample. And we have different samples that are sampling this measurement at the different redshifts, right? And when we take this thing together, we can build a picture of our cosmological model. And what we find is that there is sort of a mild, very mild 2.3 sigma tension with the CMB measurements. But more interestingly, we are finding a somewhat relevant or starting to be becoming relevant preference for a dynamical dark energy model, right? So here you can see in this bottom panel the predictions for a dynamical dark energy model. So you have these dashed lines here at 0 and -1 corresponds to constant dark energy, which means lambda CDM. So the standard cosmological model we have. And we see that our data points are going a little bit further away from that. So we're starting to see some interesting results here. So either this could help potentially explain why we're having these tensions on H naught or other things, if basically we discover that the model is not correct, right? Okay, so I see that it cannot be fully seen in this wall here, but here around this here, I think here, there is a stripe, a gray stripe, corresponding to the Schu's measurements from supernovae, just to signal this tension of the late or early type versus late type measurements of H naught. So this is indicating that possibly there are some problems with the model. Still, we cannot though discard that there are problems with any of the data sets. But so far we haven't found anything. Okay, so these are the great. These results are looking very good. But what next? What can we do next? So the idea there are better modeling choices, so we could improve redshift errors. For instance, we have published a paper explaining or understanding a little bit more the effect of possible redshift errors in the quasars that are then translated into our measurements. We could have better explanation of the distortion matrix. So this is a procedure that occurs because we have to fit the quasar continuum. And this fit is mixing all the deltas from the single quasar. Then this we model again. So we could have better modeling, better understanding here. There are other things like high column density absorbers that could be better understood, damped Lyman alpha absorbers, for instance, or in general, like higher density objects that could have an impact on a Lyman alpha forest. We could also, but these are sort of, so let's say, fine-tuning what we already know, or like going a little bit deeper in understanding. But also we are now in Lyman alpha trying to do full shape analysis, and in the next few weeks, months, we'll have some first results out from DESI. And in these measurements, we are taking the entire shape of the power spectrum of the correlation function, not just the position of the BAO peak, but also the shape of the entire correlation function. And this allows us to do some Alko-Paczynski test, for instance, which tells us whether or not we are measuring the right cosmology across and along the right of sign. So this is giving us extra information and will hopefully help settle some things. But then the other thing that we could do, and it's what I'm more interested in talking here, is using other tracers. So at the beginning, again, we're losing. Sometimes this keeps happening. Yeah, but I'm not having screensaver here. Anyway, so you could use other tracers. For instance, you could have the carbon-4 forest. See, if you remember at the very beginning, maybe we can go back for a second. Here, we are typically using the Lyman alpha forest, but we could use the forest in carbon-4. What are the problems here? We have a lot less signal to noise because there is a lot less absorption. There are other problems that are related with these lines. Carbon-4 forest is carbon-4 is a doublet. So this will have an impact on a correlation function. If we want to use them, these things need to be fully understood. And then more precise modeling, and that's why I was saying earlier that if we really want to keep pushing, we need to understand more the astrophysical components or effects at low scales, small scales, right? So then the other option, instead of using carbon-4 or other forest in general, is to try to see if we can disentangle the different phases of the Lyman alpha forest. So there are galaxies that are seen in absorption within the Lyman alpha forest. And this is sort of what my title of the talk was about, and this is now what I'm going to be talking about in this last 15 or 10 to 15 minutes. So this is the idea. So this is sort of an older version of the same animation that I showed. I just took a snapshot where the line of sight is going close to a galaxy. What happens then? So in galaxies, we have a lot of gas, right? And typically, well, you could go through a very dense region. If you go through regions that have like more than 2 times 10 to the 20 centimeters to the minus 2 in column density, then what happens is that basically you deplete all the atoms, all the photons, all Lyman alpha photons, and then the gas becomes self-shielded. And this can be seen in the spectra as this trough, as this huge absorption here with characteristic damping wings. These are called damped Lyman alpha absorbers, right? And this is one of the contaminants that we have. Whenever we can find them, we can just remove them. Now, these objects are interesting in themselves because they are also tracing the dark matter structure. They are known to be associated with galaxies. And then if we just have a big enough sample of these objects, then you could just do another correlation function and get extra information. The problem is that there are not enough objects of them. And why is that? Can be somewhat hinted in this simulation here. So this is coming from the ENSO simulation in the Agora project. This is a snapshot, and you can see sort of the galaxy. And you can see color-coded the density. The actual values don't really matter. The idea that I want to show here is that the more blue, the more dense the galaxy, right? So if your line of sight is crossing somewhere close to this like filamentary structure, closer to the center of a galaxy or to the streams of gas that is being accreted, then you are more likely to find a damped Lyman alpha absorber, right? This feature here that I was mentioning before. And you can see that in this simulation, we extracted like a line of sight from this point, say, and we get a spec that looks something like this. You can see the similarity of this absorption line here and this absorption line here, right? So we are seeing these damped Lyman alpha absorbers. However, what happens when we are going through some other place in the galaxy where we are not having this is not as colored. So this is happening way more often than in the LAs. And we are still finding sort of a signal. So we find a signal that it's very, very much harder to decipher. Basically, we are having zero flux in this 300 kilometers per second width, right? And that's more or less it. Except that, okay, let's say we can take these things out from the forest and then measure the correlation function. And can we successfully find these objects? This is the question, because if we find these objects and we show that they are the same as the LAs, now our sample is becoming much, much bigger, and we can start doing something with them. Instead of just removing and throwing them away, we could just have a new tracer and just add them to the standard BAO analysis, right? So this is what we tried to do already in SDSS data, and this is showing the measurements from SDSS data. You can see hints again, like the different panels now are showing these different wedges that I was showing before, right? So these are close to the line of sight. This is away from the line of sight, and you can see that we cannot still measure this BAO from this data. Of course, the signal to noise is not as high, right? More things here, like it is important whether or not you mask these objects from the Lyman alpha forest when you're computing them. Because for example, the mean absorption will change if you remove all the forest, all the objects that have zero flux, right? The mean forest will go up, and therefore the entirety of the forest will change. But in terms of the correlation, it is not that important. We can see that the difference is seen between the black and the red points. So now what we saw with SDSS data is that there were some problems that we were anticipating, and we still cannot use this in the analysis because, for instance, the modeling was giving us very bad chi-squares, and there were some features that we didn't understand. We thought at the time, now it's not so clear anymore, but we thought at the time that the metal contamination modeling that we were assuming was too simple. And because we have high redshift precision for these objects, we simply were breaking the model, and it was not capable of explaining the observations. Now, the idea is that we need to add these objects into mocks, and this is something that we are doing also in WEAV/DESD with some people like Manuel Herrera Fernandez, Ruiz Herrera Bernal, where basically we're taking the mocks that we built for DESD and for SDSS, and we are adding this absorption. And this way, we are not only adding this absorption from SVLAs, but also, more importantly, the associated metal contamination, which is what we think was breaking. Now, our results in the mocks are still preliminary. I'm not going to show them today, but they're somewhat puzzling because we are not seeing the problems that we were seeing before with the metal model. But we'll see. One of the ideas is that just redo this measurement using DESI data, because data will be much better, and we also have advanced significantly in the measurement of the correlation function and our understanding of these correlation functions. But what's perhaps more important is that for these objects, we can build a stack, or take all the strong blended Lyman alpha absorbers, we shift it to the redshift, and we stack them together. Now, noise gets beaten down to the extreme, and we can see that we can detect many absorption lines by metals. So this will help us better understand the metal contamination, because these metals are now being introduced in the mocks in a self-consistent way, whereas before we introduced these objects, the metals were just painted on the mocks, right? So now these tags are also important because they are telling us about the actual population that we are studying. So we did some population analysis on these lines based on the equivalent width of these objects. We measured the velocity dispersions. We also measured the bias of these traces, and we found that everything is consistent with them being in the same populations as damped Lyman alpha absorbers. So the whole picture seems to point to the direction that we are seeing a population of galaxies in absorption. Right? So this population of galaxies, we're talking about from hundreds of thousands to maybe 1 million galaxies already in data that is already being observed. That's at redshift higher than 2.1, at least, because that's where we enter the spectra in quasars. And it's like a region in redshift where there are not that many galaxies. So this would be like, if we can confirm that these are indeed galaxies, this would be like a huge population where we could extract a lot of information for cosmology and also for other endeavors. Like, for instance, trying to understand what's driving the evolution of galaxies. So maybe already going to the take-home message before moving to questions. DESIDR2 BAO results are out, so they're looking great. There's still some tension with CMB measurements using LCDM, but the more important or maybe more interesting result is that we're seeing a stronger preference for dynamical dark energy as opposed to standard LCDM. So this we will need to see with the future data releases what's going on. If this goes away, it's just a statistical fluke, or if it has come to stay. We're still not really clear on that. But besides this BAO, we have this new framework that we're trying to show. We're trying to prove if we can find galaxies within the forest, which would help us discriminate between different phases in the completely intergalactic medium and circumgalactic medium phases of the Lyman alpha forest. and then measure BAO with this new tracer. We can see that in a preliminary test, they're showing that we could get like an extra 8% in decrease in the error bars with the data that we already have, which would be a significant improvement. And then also another thing that could be interesting is to using these probes, these stacks that I was showing, to try to put constraints on resolution simulations, which typically are evolved all the way to redshift 0, but then we would be giving them constraints at redshift 2.1, 2.2, or even a little bit higher. And that's it. If you have questions, I'm happy to take them. Just let me just point a little bit to these credits from DESI and other institutions. So thanks for your attention. And if you have questions, I'm happy to answer them.
Thank you, Ignasi. So, as he said, questions.
I'm not from the field, so I ask a basic question.
Sure.
The BAO, you said you need to set somewhere a scale.
Mm-hmm.
Typically, or I guess people use the cosmic microwave background. The BAO is a three-dimensional thing, but the cosmic microwave background, you only have a two-dimensional snapshot. How makes it that
Right,
it
so
must make it difficult to find the scale and the cosmic microwave.
so this baryon acoustic oscillation scale is seen in the power spectrum or in the correlation function, right, of the galaxies, which is not a 3D 3D measurement. So you're imagining like a 3D thing, but we're really like getting a chunk of redshift, and then compressing everything in the correlation function.
But you measured it.
Right, so the idea is that you measure the position of galaxies, right? So we have one at a given redshift, like of course redshift slice, but you have one galaxy here, and you say, so how many galaxies do I have at 1 megaparsecs from these galaxies, right? So because galaxies cluster together, you will have many, several. Then as you go away, you expect this to be decreasing, right? Because at some point it's just random, it's not correlated. So what you see is that at 100 megaparsecs, this is an excess that you would otherwise not be able to explain.
How do you set the scale with the cosmic microwave background?
Well, so in the cosmic microwave background, so there is this sound horizon scale. So this is one of the parameters that they use to model the.
Because you don't have redshift information on cosmic microwave background. That's basically
the
universe clustered into a single piece.
Into a single moment. But you have many more modes that are entering. You can so the matter is like say everywhere, right? So you can have more precise measurements of different modes, and then you have like this Planck figure that you've already probably seen many times with a lot of peaks, and then in your model, these peaks, the sound horizon plays a role in where these peaks are exactly placed, right? So this would be one way, but you don't need to use that one. So this, you could use, if you wanted, you could use like Hubble H0 measurements from supernovae, for instance, and you could just find. So the matter is that you measure the BAO scale at many redshifts, and as long as you find in one case you can measure the actual physical distance, then you can translate everything everywhere, right? So in the CMB, you do this through modeling purely because what you're saying is everything is compressed, but you could have them somewhere else. Like for instance, if you take Big Bang nucleosynthesis probes, the amount of elements that you have is somewhat setting, talking about the densities, and then you could have an estimate again through different modeling, but modeling still of the sound horizon. I mean, this scale is driven by the sound speed in the medium. So if you could somehow measure the sound speed, then you can measure also the scale.
I'm curious about the precision addresses that you have and why it is important to understand the error or the estimation of the error.
Right. So one thing I did not explain too much because there are many, like it's a little bit maybe too technical, but is that, so the way it works is we first identify quasars, right? And now from these quasars, we need to know where they are placed. So we are measuring the the forest between, we want to measure the Lyman forest between the Lyman alpha line and the Lyman beta line. But what happens if we get the Quasar redshift wrong? So we know that these absorptions here, the absorption is fixed at like the Lyman alpha absorption, which is 1215 angstroms, right? Because this is the absorption line of hydrogen. So for each individual pixel, we have like a very precise redshift measurement. The problem is that if the Quasar redshift is not correct, which is more difficult because this is driven from or derived from the broad lines emissions, so there is some margin of error. You could be like, say that you move this peak a little bit here to the left, but you still think the peak is over there. So you're introducing this emission into your measurement.
So the problem is that in advance you don't know the Lyman alpha profile of the Quasar.
Right. So not only the Lyman alpha profile, but the fact that you don't know exactly where the peak lies.
Right.
So if the peak, if you misidentify,
The solar peak usually is clear. The
yes,
thing is that the
usually, but
profile-
there is sometimes some errors. And
the blue
so there is another problem is that like when you take this peak here, it's not as trivial to say that actually is this one, because the different peaks that you observe, and typically for this quasar you see 3 or 4 peaks. You see usually Lyman alpha, you see carbon 4, you see carbon 3, you see magnesium 2. And then if you go lower in redshift, you start seeing also H alpha and H beta. But so because you see different lines, estimating redshift is not entirely trivial because of the difference on where these lines are originated. So there are known shifts between the lines because they are generated from gas at different regions between the actual center of the galaxy and the outside. So this has more to do with the AGN modified unified model, which I'm not that expert on, but what I do know is that there are redshift, so different lines are giving you different redshifts, and it's sometimes not trivial to have this correctly assessed. Right? Of course, if you do catastrophic measurement, so if you say this Lyman alpha line, but it was carbon 4 line, then this is another thing, and this is contaminating us differently, but it's mostly noise, I would say, and this is not happening as often. The problem is when you get the redshift slightly wrong, right? And also you cannot see here, but when you take the average over many spectra, there is sort of a shape in the continuum. There are some emission lines besides the Lyman alpha from other metal species that are affecting this Lyman alpha forest. So if you get the redshift of the quasar slightly wrong, all this whole mean spectrum gets shifted, and then all this position it's going a little bit off, and then your estimates are affected by this. And we are basically trying to well, we're modeling this effect, and we think it's pretty much under control, and it doesn't have any effect on BAO parameters. But if we want to go beyond BAO and go into full shape, we really need to understand this in more depth.
The curiosity that I had, I little bit lost when you put the combining spectra and absorption from Galaxy. This is what I understood.
Yeah, this one.
That one. So
Yeah.
that means that you are, how do you get that? Also because it is very curious that you put it in some way in restaurant.
Right.
Everyone.
So you take one spectra of a quasar, right? You have the normal Lyman alpha forest, and say, oh, here is one of these strong blended Lyman alpha absorbers with one of these objects that I think is a galaxy. So now, because we are finding it in absorption in the Lyman alpha line, we know precisely which position it has. So it's absorbed at 1215, so we can convert this to redshift. And then we move this, and we say we observe it at 300 angstroms. Sorry, 3000 angstroms. Right? We can just shift this to the rest frame, shift the whole spectrum to the rest frame of that galaxy. Now we do the same with another galaxy. And then, of course, the two spectrum will not be much in the same place because, but the absorption will. The 1215 absorption here in the Lyman alpha is here. This one, sorry, I wasn't finding. So this absorption from both spectra will be in the same place because it's in the rest frame. right? And then we do this with many spectra. We're talking here from memory, it's like close to 100,000, something like this, right? And now what happens is that, of course, when you add a lot of things, you have the Lyman. This is the thing that you are detecting, but these objects have a typical distribution of metals. So these are associated with galaxies and have more metals than the normal IgM points. But all those metals will also be absorbing at the same wavelength because we're shifting everything to the rest frame. So you will see these iron lines here, for instance, you will see this line and Sirius lines over there, that all will be going in the same place. And then you will have noise on top of that, but because noise will be different in different spectra, when you have many of them, it effectively disappears when you take the average. And that's why you can see very tiny, like very clean absorption signals from different metals that would otherwise be too faint to detect individually.
Questions? Yeah, I have a question. But how can you actually decouple the galaxies from the forest, the absorption from the?
Right. This is the tricky bit, right? The thing that we are not 100% sure how to do, and also one of the things that I want to try to getting a better selection function, for instance. So what we're doing now here is we are in this spectrum, we measured the lines and we tried to estimate. So we built two population models. So say one where galaxies have a strong contribution from metals and one without, which would be more like IgM-like, if you want. And then with these two, we can explain the combination of these two models. We can explain the width of the different lines. So there are some problems with that, or maybe tentative problems, let's say. And it's that we are finding clamping scales, so of sub-parsec, which I'm not sure, honestly, I 100% believe in the results, because they seem to be like too small, way too small. We cannot even like have this in very high resolution simulations. But if this is proven right at some point, which again, I remain cautious, then this is saying that we are indeed having two populations, one which would be the true galaxies and one which would be contamination. So things that we thought were galaxies, but were still random places in the IgM. So this is still something that we need to investigate a little bit further, because again, good question what you asked, how do you distinguish? Still unknown. So the idea we have in mind is to work with simulations, very hard, as high resolution as we can get, and try to see if we can detect some pattern, maybe with help of machine learning or something, and then use these newfound patterns to refine our selection.
So I understand that the first goal is to actually detect with galaxies and the redshift and constrain the BAOs in another way. But then once you have the population, which this stack procedure, you can actually measure the properties, some properties.
Yeah, you can measure like properties of these galaxies, like what's their average metallicity in several ions. I mean, you could, even if you have a high enough sample, you could even do subgroups and then see, okay, so is this mimicking some other population of lower redshift that I see? Or is this illuminating a little bit more the evolution of star formation? Because, like, you know, metals and metal enrichment is highly linked with stellar star formation rate. So there are a lot of questions you could do, but the key thing that you need first is to convince yourself that you are really seeing galaxies here. And this is something we're working towards. And for now, everything, all the things that we have are pointing toward that direction. But I wouldn't say we are there yet. We are not, at least myself, I'm not entirely 100% convinced that we are seeing these galaxies there. That's why I still call them galaxies hidden in the forest, right? So we're starting to unveil things, and everything is looking good, but I still need to be fully convinced that what we're seeing is real.
Those properties you would measure that would be like the average.
Yes.
The average.
Of course. Yes.
Okay.
Yes, if you wanted to like measure individual points, that would be much harder because like these are usually noisy spectra. So noise levels, I mean, most of these lines wouldn't even be seen in individual spectra. So then the question is how many you have and how fine you can like bin things and still measure.
Well, you think AI try to take out something from that?
Right, so what I'm thinking AI could help us is, so right now the selection criteria is very simple. I just apply like a smoothing of the spectrum and say, whenever I have consistent zero flux of 300 and something kilometers per second, that's what I'm calling. But then if you, I mean, I can imagine that in some patterns that you would have like a consistent decrease, even though it may not look like exactly zero, from other metal lines, even though it could be a little bit hidden in the noise, but it could be picked up as a pattern. I don't know. I'm just like putting things things out, right? So the idea is that if these complex patterns could be detected potentially by an AI, then we could use that to like help refine the selection function. And one way we could know that this refinement is actually working is that you build a new catalog, you build this new plot with a new catalog, and then you repeat the two population analyses that we did. And if one of the population, sort of the no metal population is going away, and you're still basically finding yourself with one population, then you've done a good job. And the AI has helped you detect, and the selection function is much better. If you, on the other hand, find like even more mixing, then it's crap, and then you can start over and find another way. but yeah. So this would be one way to test if you're working things are working properly. But the key thing here is to like take into account at the same time the high ionization species and the low ionization species, because they are produced. A few of them are more present in the intergalactic medium, a few are more present in the circumgalactic medium. And if you can explain the measured widths for all the lines, that's where you're nailing your problem.
Another comment is, do you know, or do you think that you have already observed enough galaxies to solve the tension and to reduce the uncertainty in the measurement?
So this on SDSS data, which is where we did this first study, we already had more than 100,000. We have 4 times as much data in DESI, and it will be higher resolution already also. So then if we manage, well, it will be not, it is, they are already, we have already observed that, but well, we still need to do this analysis on DESI data. We still haven't had the time. We're too focused on improving the BAO measurements. But this is something it would be interesting to do, but we definitely have enough data. I mean, already you can see from this data point that you can see the BAO markers with the SDSS data. So this is only going to get better in terms of statistics. And then the question is whether we find something else that we understand or whether we can, I mean, we need to add them to mocks in order to make sure that we are not making a like systematic mistake or something. Because yeah, you really don't want to add systematics into your sample, because then things get a lot more complicated.
No more questions? So I think we can close the talk. Thank you very much, Ignasi, for this.
So
Stop.
great.
Great.